Hello everyone. So here we have arrived to the second part. We are discussing how to determine or how to calculate the pK values, those things for organic acids, and how can we compare two given organic compounds, which one will be more acidic, which one will be less acidic. And in the last video I have shown you that how hybridization can affect it, how inductive effect can affect it. Okay, so there I said that in this video I will be discussing for substituted benzoic acids, and there I mentioned one term, a very important term, that is ortho effect. So here in this video we will see for substituted benzoic acid how ortho effect can enable us to determine which one will be the most acidic among isomeric substituted benzoic acid. Okay, so to understand ortho effect, first we have to learn what is steric interaction. Okay, because if you don't know steric interaction you cannot understand ortho effect. So as I said earlier also, steric effect is nothing but the repulsive interaction because of scarcity of space, because of deficiency of space. In a very small space, if you try to accommodate many large groups, then they interact with each other just because of occupancy of space. It is neither electrostatic, it is not at all an electrostatic interaction. Simply because of deficiency of space, they are interacting with each other, and that interaction is repulsive in nature, and that is known as steric interaction. So in ortho effect also this steric interaction plays a key role. How? Let us see. Now here I have a model of benzoic acid. Okay, all these black atoms are carbon. You can see alternate double bonds here. Okay, you can see alternate double bonds here. These white are hydrogen. This is the C double bonded O, C single bond O, and then single bond H. So this is your COOH group, right? So this is a model of benzoic acid, correct? Now you can see this COOH group, this is a bulky group, very big group. Hydrogen is very small atom, and so there is no problem to keep this COOH in the same plane of this benzene ring. The benzene ring in this plane, this COOH is also in this plane. As a result, this pi orbital and this p orbital, they are parallel, so they are resonating. This group is pushing electron density by plus R effect, or this C double bond O, it is withdrawing electron density by minus R effect. So it can operate. Now as soon as at ortho position, instead of this hydrogen, you put a bulky substituent, that is ortho substituted benzoic acid. Suppose I have put one bulky substituent at ortho position. So if this one is also bulky and this COH is also bulky, now there will be severe steric interaction. This will undergo severe steric interaction. Now to avoid this steric interaction, what will happen? This COOH, it will go out of plane. This is the benzene ring, it was in this plane. As soon as you put some substituent at ortho position, because of severe steric interaction, this COOH group goes out of plane. As soon as it goes out of plane, this p orbital of this C double bond O remains no longer parallel with the p orbital of the benzene rings. As a result, the resonance is stopped, okay, or disturbed. So since the planarity of COOH is disturbed, the resonance is also disturbed. That means now this ring cannot effectively push the electron density to the COH group. And what is the consequence? This OH group will become highly polar because it was withdrawing electron density and that is somehow stopped, right? It is known as steric inhibition of resonance. Because of steric effect, the resonance is inhibited. And what is the final result? It is reflected in the pK value. we will see after some time the pKa values. There it will be revealed that since the planarity is disturbed and this resonance is also inhibited, the acidic strength increases very much. So because of presence of ortho substituent in benzoic acid, the acidic strength of the benzoic acid increases many times. And see, here I have not mentioned whether this ortho group, the substituent at ortho position, is electron donating or electron withdrawing. Whatever may be, whether it is electron donating or electron withdrawing, it will undergo steric interaction. So irrespective of electron donating or withdrawing, if the substituent at ortho position, it will disturb the planarity and thereby it will increase the acidity. So without judging electron donating or withdrawing effect, just see if the substituent is at ortho position for benzoic acid, then the acidic strength will be very high compared to normal benzoic acid. Now see here, I have taken 4 compounds. One is simple benzoic acid and 2, 3, 4 are 3 isomeric benzoic acid. One is ortho substituted benzoic acid, then meta substituted benzoic acid, para substituted benzoic acid. All the substitutes are identical, okay, just their positions are different. So by considering ortho effect, you don't need to think about whether this substituent is electron donating or electron withdrawing, whether it is plus I effect or minus I, plus R or minus R. You not at all have to think about that. Just see whether the substituent at ortho position or not. If it is at ortho position, irrespective of its electron donating or electron withdrawing nature, out of these 4 compounds, this one will be the most acidic, that is least pKa value. So irrespective of electron donating group or electron withdrawing group, 2, that is ortho substituted benzoic acid, will be the most acidic among these 4. So the first acid you get, which is the highest acidic or least pKa value. Now to compare these remaining 3, what should be the order? Then you again have to consider those electron donating or electron withdrawing effect. As we discussed in the last video, that more the electron withdrawing power, more acidic, and more the electron donating power, less acidic. So for 1, 3 and 4 we will proceed normally, but whenever we find any ortho substituted benzoic acid, that will be the highest acidic, because this ortho substituent, because of steric interaction, disturb the planarity. As a result, the resonance is inhibited, so it becomes the most acidic. So we will see some example with their pKa values and it will be even more clear. So our first example is benzoic acid, nitrobenzoic acid. Okay, the substituent we have taken here is nitro group. So as per ortho effect is considered, orthonitrobenzoic acid will be the most acidic among these 4. So here what are the effects? Those are operating. Number 1 is ortho effect, that is the most prominent effect, and just because of ortho effect it is the most acidic out of the 4. Other than that, what are the effect? Number 2, since it is at ortho position, it will exert its minus R effect, and that minus R effect will make this carbon containing the carboxyl group highly electron deficient. And since it is at ortho position very close, so its minus I effect will be also highly pronounced, right? So other than ortho effect, minus R and minus I effect make it the most acidic. This is also supported by the pKa value. If you see the pKa value of orthonitrobenzoic acid, it is only 2.17. Whereas for paranitrobenzoic acid, here also, since it is at para position, the minus R effect is operating. Minus I effect also, but this minus I effect will not be that much pronounced like this because it is far away. But very strong minus R effect is there. So it is again highly acidic, 3.41. Now see, if we just neglect this I effect, that is not that much strong effect, then in both the cases there are minus R effect. but still orthonitrobenzoic acid is much more acidic than paranitrobenzoic acid. So this huge difference in the pKa value 2.17 3.41, this difference in pKa value can explain only by ortho effect. This ortho effect is a very strong effect, and by ortho effect only it can make this orthonitrobenzoic acid far more acidic compared to paranitrobenzoic acid. Now when we go to metanitrobenzoic acid, there is only minus I effect, but at meta position the minus I effect will be more pronounced than the para one. However, in para, in addition, minus R effect is there, so the values are almost comparable, para being a little bit more acidic, just a little bit, just because strong minus R effect which is absent here. But this minus I effect is stronger than this minus I effect because it is closer to the COH group, and we know inductive effect diminishes with increasing distance. And then comes the benzoic acid. Clearly these three, all of them will be more acidic than benzoic acid since they are all electron withdrawing. And we have compared their electron withdrawing power here, but see the difference with orthonitrobenzoic acid. It is far more acidic than all these three, and that can be explained by ortho effect only. Okay, so we are going to our next example. Our next example is toluic acid, that is methyl substituted benzoic acid. So for orthomethyl benzoic acid or orthotoluic acid, what are the effects operating at ortho position? Ortho effect will operate. That will enhance the acidity. It will make it stronger acid than benzoic acid. However, plus I effect and hyperconjugation from ortho position, they are weakening effect. Okay, they make it less acidic because these two are electron donating effect. But see, there are two electron donating effects, only one acid enhancing effect, but this ortho effect is such a strong effect that you can simply neglect this electron donating effect. And that is why I said that you not at all need to think about whether it is electron donating or electron withdrawing. Just see whether it is at ortho position or not. If the substituent is at ortho position, surely it will be more acidic than benzoic acid. Not only that, more acidic than the isomeric benzoic acids also. So it is the most acidic, and that is revealed from the pKa value also 3.91. Then comes your benzoic acid. Now for this remaining three, what we will see, whether it is electron donating or electron withdrawing. Since methyl is electron donating group, so benzoic acid will be more acidic, then will come meta and para. Now comparing meta and para at meta position, it will show only the plus I effect. Hyperconjugation is not possible. However, at para position, this plus I effect will be a little bit weaker than this plus I effect because of increased distance. But here one additional electron donating effect is there, that is hyperconjugation. So methyl at para position is more electron donating than methyl at meta position. So meta-methyl benzoic acid or metatoluic acid is stronger than paratoluic acid. Both less acidic than benzoic acid because methyl is electron donating, but benzoic acid is less than orthotoluic acid though it is electron donating, but because of ortho effect it is the most acidic in the series, and that is experimentally observed also from the pKa values. Let us take another example. The next example is chlorobenzoic acid. Okay, and we know that when halogens are the substituents in a benzene ring, it shows minus I effect and plus R effect, and halogen is the only substituent where halogen is the only substituent for halogens only, not for other substituents. For halogens only, inductive effect is stronger than resonance effect, So here it is plus R group, that is it is donating electron density by resonance effect, and it shows minus I effect, that is withdrawing electron density by inductive effect. And for halogens only, this is very important, for all other groups resonance effect is much more stronger than inductive effect, but for halogens only inductive effect is stronger than resonance effect. And here by strong inductive effect, chlorine is withdrawing electron and by relatively weaker resonance effect it is donating electron. So what will be the net result? It will be electron withdrawing, and since chlorine is electron withdrawing, that means all orthochlorobenzoic acid, metachlorobenzoic acid and parachlorobenzoic acid all will be stronger acid than normal benzoic acid. So in this series benzoic acid is the least acidic, having the highest pKa value. Now for these three, as we know by ortho effect, orthochlorobenzoic acid will be the highest acidic. So here it is ortho effect, minus I effect, plus R effect, and that makes it highly acidic, pKa only 2.94, below 3. When you go to metachlorobenzoic acid, there is only minus I effect, because from meta position it cannot show the plus R effect, the resonance is not possible. So here this chlorine is highly electron withdrawing, and hence it has 3.83, that is more than parachloro. When you come to parachloro, again it is strongly electron withdrawing by minus I effect, but that strength is less than here. Why? Because here it can show plus R effect from para position. That plus R effect somehow diminish this electron withdrawing power. As a result, the pKa value increase a little bit, that means acidity decreases a little bit. So here orthochlorobenzoic acid greater than meta, greater than para, greater than normal benzoic acid. Now in the next example, we have taken the substituent as the hydroxyl group, OH group, okay, hydroxybenzoic acid. Now as far as hydroxyl group is concerned, it shows minus I effect because of higher electronegativity of oxygen, so that is the electron withdrawing effect. And since this oxygen has a lone pair of electrons, so it will show a plus R effect. So for OH group there is minus I effect, electron withdrawing, and electron donating plus R effect. And as I said, other than halogen, for all the groups, R effect is much stronger than I effect. So here the donating resonance effect is stronger than withdrawing inductive effect, right? Now as soon as we get the substituent at ortho position, we don't need to see whether it is donating or withdrawing. So because of ortho effect, the ortho hydroxybenzoic acid will be the most acidic, having pKa 2.98, very strong acid. Then comes the meta hydroxybenzoic acid. Why? Because since it is at meta position, it can show only minus I effect, but from meta position it cannot show plus R effect. So as a result, it becomes an electron withdrawing group. Since it is electron withdrawing, so it will be more acidic than normal benzoic acid. So after it comes normal benzoic acid, and then at para hydroxybenzoic acid, what you can see, since it is at para position, it can show both minus I effect as well as plus R effect, okay. And for OH group, we know this donating R effect is stronger than I effect, so net result is a donating effect. Since it is behaving as a electron donating group, so it becomes less acidic than benzoic acid. So in this way, what we get, ortho hydroxybenzoic acid greater than meta, greater than normal benzoic acid, greater than para. Now here this OH group, this OH hydrogen can also participate in hyperconjugation, and that will be revealed when we will be comparing OH and methoxy group OCH3 here. So that will come in the next example. So at ortho position also it can show hyperconjugation, and at para position also it can show hyperconjugation, and this hyperconjugation is also a donating effect that weakens the acid. But these two donating effects are absent in meta, it is only electron withdrawing here, so it becomes more acidic than normal benzoic acid. And ortho becomes the most acidic in spite of having two donating effects because of ortho effect. Now here it is not only ortho effect, one more thing is there, and that is already discussed in the last class, hydrogen bonding. We know that greater the stability of the conjugate base, stronger is the acid. So if you take the conjugate base COO minus here, then what happens? As soon as it dissociates, we get COO minus here. This become O minus, and this become double bonded O. And here we have the OH. Now in this conjugate base, since this O minus and this H are at close proximity, so there is chance of forming hydrogen bond. Because of this intramolecular hydrogen bonding, this conjugate base is highly stable. As a result, the corresponding acid becomes highly acidic, giving you 2.98. So for orthohydroxybenzoic acid, other than these four, the intramolecular hydrogen bonding, which causes extra stability of the conjugate base, is also one of the reason for its high acidic character. Now in this example, the substituent is the methoxy group OCH3, and again just applying the same rule, because of ortho effect, the orthomethoxybenzoic acid should be the most acidic. However, experimentally it is shown that orthomethoxy and metamethoxy, they are almost equally strong. So here the effects are ortho effect, then since it is at ortho position having lone pair, it will show plus R effect, and because oxygen is highly electronegative, it will show minus I effect, right? And for this one only minus I effect, because from meta position it cannot show the resonance effect. So what is the result? This OCH3, because of only minus I effect, is becoming electron withdrawing, and hence it is more acidic than benzoic acid. And for the paramethoxybenzoic acid, here we have minus I effect, and since it is at para position, we can have plus R effect, and here again plus R effect is stronger than minus I effect, that is common except halogen. So it is electron donating group here, so it is becoming less acidic, 4.47 compared to benzoic acid, and here at meta position it is acting as electron withdrawing group, so it is more acidic than benzoic acid. Here this OCH3, it exerts a strong plus R effect, but just because of ortho effect it becomes highly acidic, and these two becomes almost equal. That means the effect of this ortho group at ortho position is diminished by plus R effect very strongly, and hence it becomes almost equal to metamethoxybenzoic acid. Okay, and as I was saying that OH group exerts hyperconjugation. If you see the previous example of para-hydroxybenzoic acid, the pH value was, the pK value was 4.58, and here it is 4.47. That suggests that para-methoxybenzoic acid is more acidic than para-hydroxybenzoic acid. So at para position, this methoxy exerts minus I effect, this OH exerts also minus I effect. Again, this exerts plus R effect, this OH also exerts plus R effect, but still paramethoxybenzoic acid is stronger than para-hydroxybenzoic acid. That means this OH group has some extra electron donating effect that is weakening it further, and that effect is nothing but hyperconjugation. So when it comes to electron donation, OH is more electron donating when attached to benzene ring compared to OCH3 or methoxy group, and that is also revealed in electrophilic aromatic substitution reaction. This OH group activates the ring more towards electrophilic substitution than the OCH3 group. Now the next effect, that is aromaticity. Aromaticity can also regulate the acidic strength. Here I have taken three compounds, compound 1, 2 and 3. Now in these three compounds, if you are asked to determine which one will be the most acidic, so see this, we will determine it with respect to these encircled hydrogens. So here if I remove this hydrogen as H plus, then the conjugate base that is obtained will be this minus charge, one hydrogen is there. So this is your cyclopentadienyl anion, right? If I remove H plus from here, what I will get as the conjugate base, right? So this is cyclopropynyl anion, and if I remove this hydrogen as H plus here, the conjugate base obtained is cycloheptatrienyl anion, cycloheptatrienyl anion. Now from the rules of aromaticity, that is the Huckel's rule and planarity, complete conjugation, from that we know that this one is aromatic because it follow Huckel's rule, that is 4n+2 rule, that we will discuss. If you don't know it, you will see in our next video where we will discuss aromaticity. What is aromaticity? Okay, so cyclopentadienyl anion is aromatic, whereas this one is anti-aromatic because it is following 4n rule, and so this one anti-aromatic. And we know aromatic compounds are highly stable compared to even resonance. Aromaticity gives the most stable compounds, and so this conjugate base will be the most stable, and greater the stability of conjugate base, stronger is the acid. So among these three, see how aromaticity is regulating the acidic character of these three compounds. All three are hydrocarbon, all three are simply hydrocarbon, but since it gives you conjugate base and aromatic compound, so it becomes the most acidic among these three. Sometimes in your competitive exam you are given a compound and some hydrogens are marked in the same compound, and then you are asked out of this hydrogen which one will be the most acidic. Let us take one such example. Now in this example I have marked these 4 hydrogen atoms. You can see A, B, C, D, right? And you are asked among A, B, C, D which hydrogen will be the most acidic in this compound. So this hydrogen, it is connected to an sp3 hybridized carbon, the least electronegative, so very less acidic. Here this hydrogen is connected to sp hybridized. We know sp has the most electronegative character, 50% s character, so this one will be acidic. Here this hydrogen is connected to sp3, but it is connected to a highly electron withdrawing nitro group, so this one will be also acidic. So what should be the result? The result is C is the most acidic. Why? It is also connected to sp3, but see, if this hydrogen is removed as H+, if this hydrogen is removed as H+, we will get a minus charge here. As soon as we get minus charge here, this becomes aromatic, cyclopentadienyl anion. So we have sp carbon here, still this hydrogen that was connected to this sp3 carbon, which if eliminated as H+ gives you aromatic, will become the most acidic. So answer will be C. So in this way, application of aromaticity, whatever effect I have discussed, ortho effect, inductive effect, effect of hybridization, effect of aromaticity, you may have countered a question where you have to apply all the concepts in one question and you have to determine which one will be the most acidic. And now we have arrived to the last example of this video. I have already discussed in the last video this part, that is the nitrophenols. Phenol is a very weak acid, 9.95, and then we have metanitrophenol, little bit more acidic, and then ortho, then para. And here I have shown you the effect of hydrogen bonding also. This dissociable hydrogen is undergoing intramolecular hydrogen bonding with the nitro group, hence it is difficult to dissociate this hydrogen, and so the ortho becomes a little bit less acidic than the para. Now see, when I introduce one extra nitro from 7.14 to 4.0, it is even stronger acid than benzoic acid or acetic acid. Benzoic acid 4.19, acetic acid 4.76. And when I introduced one more NO2, that is 2,4,6 trinitrophenol, which is commonly known as picric acid. See what is the pK value, 0.71, below 1. Very strong acid. It is not at all a carboxylic acid, it is a phenol compound, but it is so acidic that is below 1 that it is named as picric acid. Originally it is a phenol compound, but it is named as picric acid because of its high acidic strength. So you can see how electron withdrawing effect of 3NO2 group by -I - R effect can enhance the acidity from 9.95 to 0.71. So generally we say phenols are always less acidic than carboxylic acid, but if you have sufficient numbers of suitable substituents, you can make a phenol compounds even more acidic than carboxylic acid. This one often comes as in comparison with carboxylic acid, and students often confuse. They go with that phenol compound, so it will be less acidic than carboxylic acid. No, here when we have 2NO2 or 3NO2 groups, this picric acid, this is much more acidic than carboxylic acid. Okay, next I just give you one hint about my next video, where I will be discussing a very famous example of maleic acid and fumaric acid. These are dicarboxylic acid. There are two COH group, and it has two different pKa values, pK1, pK2. pK1 for the first dissociation of the hydrogen, then pK2 for the second dissociation of hydrogen. And we will see some beautiful things about the pKa values when we will compare these two. There will come many of the effects, so I will make a separate video for these two, comparison for these two, for pK1 value and pK2 value. So stay connected, stay tuned with me, and if you are finding these lessons useful, then I ask you again, just like, comment, share and subscribe my channel. Thank you.